Hello, Mr. Claudia here, and today we will be doing a review of all things exponents. All of your exponent laws that you've learned in grade 9 and 10, we will be going over today. It'll all be summarized on this page for easy studying, and hopefully most of it will function as a review. So let's go over what is an exponent. Where do we use exponents? We use exponents when we have to, when we're multiplying the same variable over and over again. And this is the general form of an exponent, x to the power of a. Those can both be values, but in this case we're just doing a general expression. X, well, that's the base. And this small letter up here, that's the exponent. Other words you might use would be to call it a power or even an index. We use exponents to show repeated products of the same variable. So an easy way to think of this, 5 to the power of 3, that's just a short way of saying 5 times 5 times 5. If you type that into your calculator or do that in your head, it's going to give you the answer 125. But we also use it to show repeated products of variables. So x to the power of 4, well, this is just x times x times x times x. We don't know what x is, so we write x to the power of 4 because it's quicker. A quick note about BEDMAS. This is something that I always have trouble explaining to my grade 9s, my grade 10s. There's a difference between -2 squared and -2 squared. When we do to remember that difference, you can go back to BEDMAS. BEDMAS, brackets, exponents, division, multiplication, addition, subtraction. So I would always do the brackets first. So here there are no brackets, but here there is. So the bracket is -2, stays together, and then we go to exponents. So here my bracket stays together, so it's -2 squared. So it's -2 times -2. So that gives me 4. Now here, BEDMAS, there's no bracket, so I do the exponent first. Well, my exponent is to the power of 2. The minus in front is technically a -1 multiplied by 2 squared. So this is a multiplication here. That's done later. I do the exponent first. So I end up with -2 times 2. So that gives me -4. So just beware the difference there between the two. The brackets are important. Okay, let's look at negative bases. So, for example, my base, remember that's the big number on the bottom. If I had -1, oh boy, -1 to the power of 3, well, that is really going to be -1 times -1 times -1. So -1 times -1 is +1, so this is -1. And if I had -1 to the power of 4, that's going to be -1, -1, -1, -1. -1 times -1 is 1. It's negative, then it's positive, so this is +1. This is a kind of an important little pattern. A negative base to an odd exponent is always negative. So -1 to the power of 101 is going to be negative, right? Anytime it's an odd number here. This can be useful when we're doing some more difficult algebra. And a negative exponent to a positive, oh shoot, negative base to a positive exponent is always positive. Okay, so that's a little trick that we learned. Then I think in grade 10 we would have learned negative exponents. This negative exponent indicates that we must take the reciprocal. So for example, and I'll just write this in the box here, a to the power of negative n, this is really 1 over a to the n. We put it in the denominator, or technically we're doing a reciprocal. So for example, 6 to the negative 2, well, this is just 1 over 6 to the 2. We take the reciprocal. 6 to the 2 is 6 times 6. So this is 1 over 36. And I'm happy with that answer because I don't know what 1 divided by 36 is without using a calculator. Another example, we have 2 over 3 to the power of negative 3. This is why it was important we said it's a reciprocal. The negative, to get rid of the negative, I have to flip this fraction. So I get 3 over 2 to the power of 3. These two expressions are equal. Now I can solve this. This technically means 3 over 2 times 3 over 2 times 3 over 2. When you're multiplying fractions, you multiply the tops, you multiply the bottoms. So 3 times 3 times 3 gives me 27, and 2 times 2 times 2 gives me 8. Finally, there's a few special cases. So if I have 1 to the power of, say, 100, so that's going to be 1 times 1 times 1 times 1 times 1. It's always going to be 1, so that is just 1. So I have a rule then, 1 to the power of anything, a, is always 1. Another special case, if I have 0 to the power of 100, well, technically that's going to be 0 times 0 times 0 times, so that's also going to be 0. So 0 to the power of anything is also going to be 0, as long as a is greater than 0. And finally, if I have 100 to the power of 0, that's always, anything to the power of 0 is always going to be 1. So that's another special case. And hopefully you kind of familiar with these. So 1 to the power of anything is always 1. 0 to the power of 0, or sorry, 0 to the power of anything is always 0. And really the weird one is anything to the power of 0 is always 1. You can test those on your calculator if you don't believe me. There's probably one more actually I'm just going to write out, which is anything to the power of 1 is always just that anything. That kind of goes without saying. So 100 to the power of 1 is just 100. Okay, so we have what are exponents, negative exponents, and then some special cases. Now, we can't just add and subtract these things, these exponents that we've created. For example, x to the power of 2 plus x to the power of 3 does not equal x to the power of 5, and I hope you're okay with that. You've been trained and conditioned to know that this is not allowed. There are some things you can do to work with exponents, and they are through the exponent laws. So let's look at what the exponent laws are. The first one is the multiplication law. So this is a to the power of m, so an exponent, times another exponent, the same base. I can just add the exponents. I have a nice little song I learned when I learned this in grade 9, and if you see me in person you can ask me to sing that song for you. So I'm not going to sing on the computer. So if I have an exponent with the same base but different powers, I can keep the base and then add the two powers. So for example, 3 to the 5 times 3 to the 4, well, because I'm multiplying two exponents with the same base, I am allowed to use this exponent law, which is saying I can add the exponents and I get 3 to the power of 9. Similarly here, I have x to 6, x to 7. Remember, these are being multiplied together. Even though there's no multiplication symbol, I know that this is multiplication. So I can just add these. I don't have to show my work. X to the 13. Oh, Now I can do crazier things like this. How do I simplify this expression? The big thing about math in this chapter is that we're not making up any rules. So there's no secret, there's no extra thing that I haven't taught you. You have all the tools to solve this. The first tool, which you've already learned in previous years, is the distributive property. I need to multiply the thing outside the bracket by both terms. So let me just write that out. That's going to be 3x squared times x squared plus 3x squared times 2y squared. Okay, now this looks kind of like a problem up here. I have 3x squared times x squared. Well, these are being multiplied. They have the same base, so I end up with 3x to the 4. Okay, then when I do questions like this, let me look at the coefficients first. 3 times 2 is 6, and then I have x squared and y squared. I cannot add these exponents because the bases are different. So that is my simplified version. Okay, the second exponent law is very similar. This is the division law. A to the power of m divided by a to the power of n is equal to a to the power of m minus n. So if I'm dividing exponents or powers with the same base, I can subtract the exponents. So here if I have 5 to the 4 divided by 5 to the 3, well, this just becomes 5 to the 4 minus 3, which is 5 to the 1, which is just 5. Now, very rare you're going to see a division sign like this. More likely you'll see situations like this. You've been conditioned at this point to look at this and say, oh yeah, I can just subtract and I get x to the power of 4. And then we can do more difficult questions like this. I have terms on the top and bottom. Let me look at the coefficients first. 9 divided by 3 is just 3. X to the power of 4 divided by x to the power of 2. I subtract, that gives me x to the power of 2. And there's still going to be a y in the denominator. Nothing happened to it, so it's still there. Finally, our third exponent law is raising to a power. So this is if I have a to the m, so some sort of exponent raised to another exponent. I can simplify this by multiplying those two exponents. Again, don't make up math. This is only allowed if you have a situation that looks like this one here. 2 to the power of 2, all to the power of 4. Well, this means that I can multiply these two exponents. So 2 to the power of 2 times 4. That gives me 2 to the power of 8. Similarly here, I end up with m to the power of 12. And then I get to this last question. When we see all of these things raised to the power of 5, technically each one is going to be raised to the power of 5. So if I rewrote this, I'd have 2 to the power of 5, x to the power of 5, and then y squared to the power of 5. 2 to the power of 5, well, that's 2 times 2 is 4, 8, 16. Okay, so this is 32, x to the power of 5, and then this can be combined. I multiply the two, so I get y to the power of 10. So there are your grade 9 exponent laws, but with some more difficult questions. Okay, let's turn the page, and we'll finish. Before we do some more difficult practice, the last thing we would have learned sometime last year were rational exponents. And the rational exponent is basically revolves around the inverse of an exponent, or a root. So for example, if I have 3 to the squared, that gives me 9. Well, the inverse would be taking the root of 9 to get 3. So square root of 9 gives me 3. So we know this idea of square root of 9, the way we say this. We know 3 squared gives me 9. The opposite, or the inverse, is to take the square root to go back. What number multiplied by itself gives me 9? Oh, that's 3. However, we can do more complicated questions. So if we have 3 to the power of 3, 3 times 3 is 9 times 3, that's 27. So if I wanted to figure out that 3 again, I'm basically trying to imagine what number times itself 3 times gives me 27. In other words, what is the cube root of 27? And the answer to that is 3. So we call this the cube root. So this idea of taking a root, this could continue: square root, cube root, fourth root, fifth root. We can keep going. We would write the number, the root we're taking, and then the value. And another way we can write this is as a rational exponent. So let's just put this in the big box. This is kind of the last part of our exponent section, a little confusing. So the nth root of a. In other words, I could rewrite this as 27 to the third. That's the similar way of writing the cube root. I write it like this. Over here it would have been 9 to the half equals 3. So the idea of the square root, cube root, that's what we're talking about when we talk about rational exponents. So let's look at a question like this. 8 to the power of 5 over 3, and we see that and we panic because there's a fraction here. Let's rewrite this as 8 to the cube root all to the 5. Remember, if I had to work backwards to combine these, I would just multiply them together. I'd go back to this fraction. But now I can solve this because 8 to the third is really saying, what's the cube root of 8? What times itself 3 times gives me 8? Well, it would have to be a pretty small number. It would have to be 2. 2 times 2 times 2 gives me 8. So the cube root of 8 is 2. That's raised to the power of 5. So then I have 2 to the power of 5, which is 32. If you don't believe me, you could use your calculator, although you probably won't have access to your calculator on a question like this. But if I go 8 to the power of 1 divided by 3, that gives me 2. The other way I could write on my calculator is go cube root of 8. Excuse me, it gives me 2. Let's do a difficult. I wanted to jump right into some more difficult questions because I find these can be difficult, like can be overwhelming to look at. But when I see this fraction, I need to split it up into 2 parts. Because I know 27 is related to the cube root, I'm going to write it this way. So 1 over 27 to the power of 1/3 all to the power of 4. Okay, so now I distribute this. So I have 1 to the 1/3 over 27 to the 1/3 all to the power of 4. The cube root of 1, well, 1 to the power of anything is always 1. And 27, the cube root of 27. So what times itself 3 times gives me 27? Well, it's 3. And that's all to the power of 4. So I end up with 1 over 81. The thing about an exam without a calculator is that there are only so many roots you can figure out. The numbers get very large very quickly. So if you're looking at rational exponents, you'll often have pretty recognizable numbers that you see over and over again. Case in point, this one here. I have negative 125 to the power of negative 2/3. So first of all, got a lot going on here, a lot of negatives. Let's get rid of this negative here. And if you remember from the last page, a negative exponent means that you have to rewrite as a reciprocal. So this is going to become 1 over negative 125 over 2/3. Look at what I've done. I've just gotten rid of this negative by putting the whole thing in the denominator. Now, the next thing I want to tackle is this rational exponent. Let me do the cube root first. So I'm going to have 1 over negative 125 to the power of 1 over 3 all to the power of 2. Again, why do I choose to do it not this way around and not negative 125 squared to the power of 1/3. Well, negative 125 squared would be really hard to do in my head. And I suspect that the cube root of 125 is something I know. In fact, the cube root of negative 125 is, or of 125 is 5. So I have 1 over, actually it's negative 5, and then this is squared. Remember we talked about with negative exponents. Negative exponent, I have to, it only works out if it's a cube root. If I couldn't take a square root of a negative number, but fortunately I can take a cube root of a negative number, because negative 5 times negative 5 times negative 5 gives me negative 125. And now I can square this and I get 1 over 25. Whew. Okay, so now I have about 9 more difficult questions. I tried to choose some challenging ones that wouldn't waste your time. What I'd recommend to do is try going through these on your own. This will give you a chance to see where you're rusty, give it a try yourself, and then you can look at my solutions. And then you can, when looking at the homework tonight, can really see the sections you need to work on. So pause the video now and try these questions on your own. Okay, now that you've attempted all these questions on your own, let's go through them and see all the weird math things that happen. The one thing I'm going to continue to say in this lesson is do not make up any math here. You know all the rules. There are 3 exponent laws, some strategies for dealing with negative exponents and rational exponents. That's it, right? There's no other magical things you can do. So let's start with this first question. This square, well, first of all, to get rid of that square, that gets distributed to all the things inside this bracket. So the square goes to the p squared, the 3, the q cubed, and also goes to this negative in front. That's technically a negative 1. You want me to write that in? It's technically a negative 1. So I end up with negative 1 squared. I end up with 3 squared. P squared squared all over Q3 squared. Now this question is a lot easier. Negative 1, well, to the power of 2, that's automatically going to be positive 1. 3 squared is 9. Here I multiply my exponents, and then here I multiply my exponents. Next question. Similar problem, except I don't like this negative. What's the negative mean again? If you go back, negative is you have to take a reciprocal. So let me go here and take a reciprocal. So I'm going to get rid of negative by rewriting it with the numerator as the denominator and vice versa. Okay, step 1 complete. Now this is just like my last question. I have to distribute this 1/3 to each element in the bracket there. So I end up with 216 to the power of 1/3 y to the power of 3 to the power of 1/3 over 125 to the power of 1/3 x to the 6 over 1/3. Okay, and now let's do this. So what number times itself 3 times is 216? Again, there's only so many. This is getting into the upper level of what I should know off the top of my head. 5 times 5 is 25 times 5 is 125. 6 times 6 is 36. Ooh, 36 times 6 is indeed 216. So this answer has to be 6. Here, y to the power, okay, so I have to multiply these. So 3 times 1 over 3, these cancel out and just gives me y. The cube root of 125 is 5. And x to the 6 times 1/3, or divided by 3, is going to be x squared. Okay, let's keep going. Oh, look at how overwhelming these questions are. So I have a square here on the top. That goes to these 2 things. And then I have a square here on the bottom. That goes to these 2 things. So I end up with 5 x squared squared y squared 5 squared x squared all squared. So that gives me 5x to the 4 y squared over 25x to the 4. Okay, I should simplify this a little bit. 5 divided by 125. Well, hopefully you remember, again, we can look at the coefficients on their own. Hopefully you remember from what you did in grade school with fractions. 5 goes into itself once, 5 goes into 25 5 times. X to the power of 4 divided by x to the power of 4. Well, technically I can subtract these, right? X to the power of 4, I can subtract the exponents. That gives me x to the power of 0. Which is just, anything to the power of 0 is just 1. So I end up, and then I have y squared. So I end up with y squared over 5. Because the x to the power of 4's cancel each other out, and I'm just left with 5 on the denominator. Okay, let's keep going. 20 a to the power of a divided by 2 to the power of a. Okay, so can I subtract these exponents? Well, no, I can't do anything because the bases are different. There is a trick I could do, though. I could split this 20 into 2 times 10. And then both of these, this a would be distributed to both of these things. So I would end up with 2 to the power of a times 10 to the power of a over 2 to the power of a. Now these two things cancel each other out, so I end up with 10 to the power of a. I suppose another way you could have done this one would have been to recognize that you have 20 over 2 all to the a, so that becomes 10 to the a. Similarly, we have a few different ways we could solve this next one. You could look at this and say, okay, well, I have 5 to the n plus 1. Oh, I have the same base. This is technically to the power of 1, so I can subtract. So I have an n plus 1, and I subtract the exponent in the denominator. So I end up with 5 to the power of n. Or another way I could solve this question would be to recognize that, okay, well, 5 to the n plus 1, that's really 5 to the n times 5 to the 1 over 5 to the 1. These cancel each other out, so I'm left with 5 to the power of n. Whichever way works, you're not making up math in any of them, but make sure you're careful with a question like that. Question F. We have 2 to the power of n, so here we're going to use that trick we just did. I can't really divide much in here, but I can rewrite this as 2 to the power of n plus 2 times 6 to the power of n over 2 to the n. So I get 2 to the n plus 2 to the n, 6 to the n over 2 to the n, because that n applies to both of these things. Now, there's again a few ways to solve it from here. What I kind of see is I would factor out 2 to the n, and I'm left with 1 plus 6 to the n over 2 to the n. 2 to the n's cancel out, so I'm left with 1 plus 6 to the n. That's a tricky question, and it does a bunch of things, right? Because we have to recognize this, but then we also have to factor out the 2 to the power of n. If I divide this by 2 to the n, I'm left with 1. If I divide this by 2 to the n, I'm left with 6n. Okay, and we have some questions down here. This is going to, hopefully you'll recognize that this, I need to use the distributive property. So when I multiply this together, I'm just going to rewrite it. I have 2 to the negative x, 2 to the 2x, plus 2 to the negative x, 2 to the x. This gives me, okay, well, to combine these, I'm going to add the exponents. So I have negative x plus 2x. Notice how this question, I'm taking my time a bit and I'm showing my steps. looking at this, I get confused, but then I remember, oh, they have the same base, so I'm just going to add the exponents. And over here, they have the same base, so I'm just going to add the exponents. Taking my time, I end up with negative x plus 2x. That just gives me 2 to the x plus negative x plus 2 to the 0. Remember, anything to the power of 0 is 1, so I end up with 2 to the x plus 1. We look at a question like this and we panic and say, I never learned anything like this. But you know all of this. This is just a FOIL situation. So I need to multiply this by this, and then I need to do the outside the second value outside, or the inside. So let's write out each step. So I have root x times root x, and then I have minus 2 root x, and then I have plus 2 root x, and then I have plus 2 and minus 2. Okay, well, square root of x times square root of x. Let me write this with my rational. So x to the half times x to the half minus, minus 2x's plus, or sorry, minus 2 of something plus 2 of something. So minus 2 square root x plus 2 square root x. Well, they add up to 0. And then I have 2 times negative 2, which is minus 4. When I'm multiplying two exponents with the same base, I can just add the exponent. So half plus half gives me 1. So that's x minus 4. I probably could have gone, I should know the square root of x times the square root of x is just x. And if you look at this, you see it's actually a difference of squares that someone's done. So they've done square root of this plus square root of this times square root of this minus square root of this. But we use our exponent laws to figure it out. Finally, this last question. I hope you looked at this and maybe thought for a second, oh, I need to distribute the square to both of these terms. And then hopefully you remembered, no, I can't do that. I'm allowed to distribute this square to everything inside the bracket because they're all being multiplied, but not here. So then hopefully you remembered, hey, I'm not going to make up math. I learned last year in my quadratics chapter, I can rewrite this like this. Now when I've done that, then I can see, oh, this is just FOIL. So I'm going to do my outside and my inside. And again, I'll show all my steps because I find this confusing. So I have 2x times 2x. I have 5 times 2 to the x. I have another one, 5 to the x. And I have 5 times 5. I'm just going to write 25 because I'm running out of space. Now, in this case, they have the same base, so I just add the exponents. Here I have 5 of something, so 5 to the power of x, and 5 of something. I always say, like, oh, if you have 5 apples plus 5 more apples, well, how many apples do you have? 10 apples. So I have 10 of 2 to the power of x and plus 25. So this is x plus x is 2 to the power of 2x plus 10 times 2 to the x plus 25. And that's the most simplified form I can do there. Okay, so that's everything for our review of exponent laws. I hope there was something new here, or some challenge questions, but I hope for the most part it kind of rejuvenated your memory. Your homework for this week, or for this lesson, is page 104, number 1 to 3, 106, number 1 to 2, and 107, number 1 to 2. And again, I'm just going to make that note, don't make up math today or anywhere in this chapter. As we get into logarithms, there's going to be a tendency to make up math. But remember the questions down here. We used all the skills that you've learned before. You don't ever make up math. So just kind of keep coming back to that. Use the things you know. Good luck with that, and we'll see you next time.